Excellent. So where was I? Pausing for dramatic after my gut scale axion joke and you're all laughing at it. Thank you. We're back on track. So my research program is divided between the search for axion dark matter and ironically the search for neutrino double beta decay. So Giorgio and I are well aligned with this. And the power of these searches is going after these big questions of what is dark matter and why is there more matter than antimatter. And so for me, I really like the connection in both of these topics to new gut scale physics, the Majorana neutrino up at a gut scale, and nano EV gut scale axions. And so for this workshop, this is the beyond the standard model physics that interests me because we know something has to be kind of happening at this grand unification scale. So what do we use in my lab? It's a lot of photodetectors. I like quantum dots. I like full-size bulk crystals, magnets, and dilution refrigerators. And so on the double beta decay side, what I'm interested in is bolometric detection. So these are crystals, macroscopic crystals cooled down to millikelvin temperatures, and you're measuring a heat signature, and it's scintillating bolometers, the heat and the light signature. And so the detector that does this is the Cori detector. It's 1 cubic meter of tellurium dioxide crystals cooled down to millikelvin temperatures. And as we discussed yesterday, yeah, so it's a beautiful detector. And so we were discussing over lunch the crystal growth that's needed for the atomic, for the thorium clock, is using the same crystal growth techniques that you need to do these 1 ton of tellurium dioxide crystals instrumented at 10 millikelvin. And so this is really literally using Avogadro's number to give you the power to measure things at a power with half-lives at 10 to the 26 years. The next version of these experiments is going to 10 to the 27 years, and eventually, I'm hoping this technology can bring us to 10 to the 28 years and a definitive search for the Majorana neutrino. And I thought that this was, it's such a pretty detector. I really think it should win some beauty prizes for this. And so then this goes into my love of all sorts of crystals that you could instrument in this way. And so more pretty pictures on the crystal front. So this talk, though, is about dark matter. And where does the nano EV or gut scale axion fit into this wide realm of dark matter? And so I think there was already some comment today that possibly getting a little frustrated in the search for dark matter, or that it's not clear where all these particles fit in to the zoo of dark matter. And so I might have young children that have read Curious George Goes to the Zoo. And so hence, this is actually how I think of dark matter it is a zoo. And we are been looking for elephants for a very long time. And the question is, what are the other candidates there? And what are the experimental techniques to go after them? And in my mind, the experimental techniques, every animal getting its own balloon. But that's a good way to think about what's going on here. So, as you move down in dark matter parameter space, what we're often doing is going to lighter and lighter masses. And so for this workshop, as we start talking about the atomic techniques, those are going after often the most lightest candidates. And so as you move down from the classic WIMP at 100 DeV or so, you move into this sort of light particle dark matter parameter space where there's a huge effort within the field to understand how do you even make these measurements down to about 1 keV. And so it's lower and lower effectively band gaps down to where you're breaking up Cooper pairs. And you might notice that in red is an idea I like, but as you keep going down, there's also a lot of exotic materials that overlap with some discussions on how do you actually simulate these materials. Going even farther down, at 1 eV, you hit the wave particle divide, and where you're starting to treat the dark matter actually as waves. And you heard from Masha, I believe, earlier today about D phase and the dielectric telescopes. And going even further down into this regime is really, you're in this wave dark matter regime. And so anything less than 1 eV is wave-like dark matter. It can be divided up into its behavior under CP. So you have your pseudoscalars, your scalars, and your vectors. All of these light dark matter candidates will be produced athermally in their early universe. And so they all have this athermal cosmic history. They were never connected to the cosmos thermally in the early universe. And so it gets you around a lot of the constraints. And the detection technique, you're going to be using some sort of coherent interaction with your detector and some sort of precision measurement technique. This is the overlap there. The most famous candidate in this group is the QCD axion. And that is providing much of the benchmarks in this parameter space. I would note, though, that there's been a huge amount of thought into all of the other possibilities of getting down into this parameter space. And I would point to a paper, and I'll bring it up later in the talk, that came out of the SNOMAS process led by Mariana Safranova and Swati Singh. So the QCD axion, it was introduced to preserve CP symmetry and the strong interaction. It is a pseudo Mann-Goldstone boson. You're adding a new U1 symmetry to the standard model. You break it, you make these things in the early universe. It can couple to photons, nucleons, and electrons. And you have these two broad categories of models that introduce new heavy quarks or new Higgs fields. And the plot you see on the right is the one that every single axion talk you ever will see will show you. And so on the x-axis is the mass of the axion. On the y-axis is the coupling to the standard model. It's often the coupling of photons. We'll talk about that in a second. And then these two bands, which just give you a broad category of models to look for. And so the whole field is looking for these DFSC axes. And that's what we're up to. There is a whole other category of particles, these so-called axion-like particles. They too are made by breaking symmetries in higher order theories, and they're even less constrained of where they would show up in here. And so what's nice is we might run into one of these characters before we hit the QCD axion. In fact, that would be my dream, in that you've actually disrupted some sort of real new physics that is not the standard model, because we're all a little bit higher than the standard model. I have to warn you, though, in axion land, we get really lazy and we talk about axions as either the axion-like particles or the QCD axion, and I'll be guilty of this too. But what you should take out of this is that for the axions, there's roughly a parameter space in mass from 10 to the minus 12 eV to 1 eV, which we believe is the really optimal place to search and where much of the focus of the field has been. And it does range from tabletops, they're often cold tabletops, down to something that's quite large, which is the gut scale searches for axions. So how do you actually build a detector? If you're coming from particle land, you're used to these heavy dark matter detectors. If you're in axion land, you need to really get comfortable with the wave. In other audiences, this is more important. I feel like a lot of people are very comfortable with waves in this audience. And so what we're looking for, what the signal looking for, is this field that is oscillating with a frequency at the mass of the axion. You don't know a priori what the mass is, but you're looking for this very, very narrow line shape within and above your noise. In fact, has a very characteristic shape, which is nice from the analysis perspective. You are looking for a very narrow peak with a hump to higher frequencies, a shoulder, and that's due to the velocity distribution of the axion. So if you find a peak in your data, it has to be very unique and it has to have this very distinctive signature of the shape of the axion dark matter. So the question you might ask is, there's any theoretical preferences within this regime? And so there is some question of when your axions were made. Some were made before inflation. Sorry, if they were made before inflation, then the universe effectively mixes up the whole universe and there's not many constraints on the axion. I would note that that is where nano EV gut scale axions live. So if you detect a nano EV axion, you're detecting something that was created before inflation, and that would be really awesome. So that's it. There's also the post-inflation axions. These are the classic axions that people like ADMX have been looking for a long time. They're much more constrained. And in fact, if you talk to people like Ben Safdie and other groups, you can actually calculate this from first principles if you have a lot of computing. And a lot of computing is what has been difficult to come by until recently. There's also constraints coming from other places, and with Masha in the front row here, actually the rotation of black holes sets bounds. And that's really what's sort of setting that 10 to the minus 12, even though there is parameter space below it. And so that's kind of a constraint coming from both astrophysics and from detector technology. So going back to how do we actually detect these things? If you're adding a particle to the standard model, you have the ability to add all of the couplings to the standard model. And so this is what you get to add to the standard model. So you have the coupling to photons, you have the coupling to the nucleon EM, the coupling to axial nuclear moment, and the coupling to axial electron moment. Those other three couplings, there are experimental ideas of how to go about it. This is mainly the Casper program of Alex Shishkov and Nima Butker. I would have to note that the techniques are more difficult, not for this audience, I know. but it is not as clear as the coupling to photons of how you would go about doing it and what the experimental issues is. Coupling, measuring photons is the easiest thing we can possibly do. And from a particle physics perspective, it's the cleanest thing to do. And I'm wearing my nuclear physics hat, and Giorgio said the same thing earlier. If you can avoid QCD itself, please avoid it. And you would prefer to do the photon measurement. And so that's why I really see the photons is where you start, but you really want to do the R&D on these other techniques, because as soon as you detect an axion, you're going to ask what those couplings are, and that will tell you what you're dealing with, whether you're dealing with an ALP or whether you're dealing with the true QCD axion. And man, would that be a really fun day. Okay, so if you're doing the coupling to photons, you're modifying Maxwell's equations, and this is what you get here. You neglect the terms that are proportional to the gradient of the axion field because they're going to be small. And so basically what you're doing is modifying Ampere's law. And for those of you who knew that I had to leave yesterday afternoon to teach intro E&M at MIT, this is what I love about Axions, is that it's actually very accessible, even to first-year students. And so you take Ampere's law in 3 different regimes. The quasi-static regime, where the wavelength of your particle is much, much bigger than your detector, you're dealing with effective currents. And you can actually, to first order, do these calculations as a first-year student at MIT. The second regime is this regime where the wavelength of your photon is on the order of your detector. This is the cavity regime. And so these are some nice advanced E&M problems, or Jackson problems. And then the hardest regime is the radiation regime, where the wavelength is much, much smaller than your experiment, and you're actually forcing the production of photons. These calculations are difficult, and there is still within the community some arguments of whether anyone has gotten them right, but that's where you are. Some level of how much E&M you really want to do and want to love. So where are we? So this is where the field is as a whole. I probably should have grabbed it a little bit earlier. So you have the classic, once again, this is the classic plot, mass axion versus GA gamma gamma. You have a bunch of experiments that have started to push into this benchmark regime at DFSZ. These are the classic cavity regimes, and I would say these are very large tables. It does fit into a lab at the University of Washington, and starting some other cavity-based experiments going up to higher frequencies. I would note and we're going to talk more about that sort of nano EV regime where my own experiment lies. You'll also see on here a lot of bounds that are coming from astrophysics, from cosmology, and those bounds are beginning to be overcome by actual lab measurements. Cool. So as a field, where were we as of 10 years ago? We had nothing that was actually probing the interesting parameter space. Now we have several experiments that are pushing into this interesting parameter space. And the question is, how do you cover this and do this definitive measurement from 10 to the minus 12 all the way through 1 eV? So there are 2 experiments that are waiting for their DOE funding. I don't know how to put it any other way. There was a big process, the Dark Matter New Initiative, and 2 Axion experiments, other dark matter experiments were chosen to go ahead. It's my own DM radiometer cubed, which we'll talk about more, and ADM XEFR. And they're going after the 2 areas that you see there down to DFSC. The question in the field is really how to cover the rest of it. And so what you're talking about is doing better with your cryogenic infrastructure, high magnetic fields, high Q cavities, and the beyond the standard quantum limit enabled readout. And so that is how you make definitive measurements here. And the field as a whole is really trying to understand how to do it. And so when we're talking about BSQL readouts, we're really talking about the sort of classic squeezing. And so at high frequencies above 1 gigahertz, you're talking about the classic squeezing, the traveling parametric amplifiers, or moving into photon counting for things like Ray. At below 1 gigahertz, you've moved into a regime that's dominated by back action. And so this is where Kent Irwin's group is working on these RQUs to do the beyond the standard quantum limit readout. And so when you're talking about axion searches, we actually move into different parameter space for the BSQL readout. And so when you're feeling like there's a lot of balloons with lots of zoo animals, it's because not only are you seeing different detection techniques, different cavities, geometries, you're also seeing different readout schemes in order to go beyond the standard quantum limit. And so that is the full zoo of axion experiments. And I think there's even some more I could have listed, but that gives you an idea of how we're going to try to get at this. I make predictions about like how many we're actually going to need, and it's fun to do. So we have these in sort of summary at this point in the talk before I dive into what I think is the right solution for this. We have two cosmologies. We have the post-inflation and the pre-inflation axions. We have three frequency regimes dictated by electricity and magnetism. And we have three noise regimes, which dictates your VSQL readout. And so I predict that there's going to be about 5 experiments that are needed to cover these 12 orders of magnitude. And that's what the field is doing. And so you're going to hear about my work, which is 1 or 2, depending on how you count it, of the experiments that we need to do this measurement. And before I go on, just to sort of reiterate why we're so excited and why we need a suite of new dark matter experiments. We always talk about exclusions. We could actually discover something, and this discovery should have actual impact. So if we discover something in this cavity regime, we know that the dark matter was made after inflation, and we have predictions about beyond the standard model physics of new quarks and new phases. And what you would do next is you would do the Casper program, and you would try to measure these couplings. What you'd also do is try to measure the line shape and actually do a precision measurement of the astronomy, the astrophysics of dark matter. You would have sensitivity to the dark matter density and flows and streams of dark matter. The axion discovery in this parameter space would tell you about an axion that's made before inflation, and you would have your first hint of what particle physics is doing in that time scale of the universe. And so, once again, this is my bias. This is what I would really like. What would be really neat is there should be CMB signatures of any extra particles before inflation, and you could end up with some very interesting tension between what we've seen in the lab on Earth and what CMB is telling us. And it would tell you something about cosmology, not just the standard model. And then once again, you can test the electron and the nuclear couplings, and you can explore the halo structure with details of the line shape. This is actually, I don't know, I go back and forth between the straight up axion, QCD axion, and the axion-like particle. The other option is you hit something well before we hit these very large experiments and we discover an axion-like particle. And that would be awesome because this would not be any simple extension to the standard model. This would be some much higher order theory. A lot of the astrophysics would be the same, and you definitely would want to go ahead and test those nuclear and electron couplings. So I hope I've convinced you of why there's a whole bunch of people going after these different zoo animals with different balloons, and maybe a little bit of an idea of what these different balloons and zoo animals are. But that is why you've heard so much from dark matter asking for this new parameter space to go search. It isn't that we're on a wild goose chase. We actually have an idea of which other animals at the zoo we would like to go visit, and that the consequences for beyond the standard model physics would be very large for these discoveries. These are not simple extensions to the standard model. So where is my work, and what could you go see if you wanted to go down to MIT early next week? It's the abracadabra experiment. And so this is a demonstrator scale experiment. I'm like, that was good timing. And it actually stands for something. Thank you, Jesse Baylor. It's a broadband or resonant approach to cosmic action detection with an amplifying B field ring apparatus. It is the best acronym. Oh, yes. It's telling you exactly what the experiment is. And this is a tabletop experiment if your tabletop is in a dilution refrigerator. And so what is it going after? And I gave away, I'm really interested in this pre-inflation axion, this nano EV axion, this gut scale axion. I think I am very convinced by the physics case for that one. So what is the B field ring apparatus that we need to go after this? It is a toroidal magnet, and so this is from the original PRL that was put forward by Yoni Khan, Ben Softy, and Jesse Baylor. Your donut, your toroid in space, the axion, due to Ampere's law, couples to the B field, and via the simple right-hand rule, and when it's earlier in the afternoon, I make everyone do the right-hand rule of the oscillating current in the direction of the B field, curl your fingers, and you get a real magnetic field up to the center of the toroid, where classically there shouldn't be one. And so from an experimental design perspective, it's a beautiful signal because it should be a zero background measurement. Obviously, nature is never that kind, nor experimental precision, but that's what we're looking for, the axion signal up through the center. And so remind you that this is a very narrow signal that we're looking for over a noise floor. So in order to build this, this was an NSF Eager Award for the magnet, a dilution refrigerator in my lab, a squid current sensor that's off the shelf from Magnicon, and some vibration and some warm and cold shielding. And so this is the actual building of the magnet. And so you're building up the magnet supports with these Delrin structure, this mandrel, and then you wrap the wire around it. This was done by SSI, which is a magnet company that is about 10 miles that way. And then that's it installed in the dilution refrigerator. And so the first installation didn't work because these experiments never worked the first time. And so a little surgery was done on the magnet to move the wire pickup loop a little farther away from the magnet, probably due to stray magnetic fields. And then we also did some work on isolating the whole system from the rest of the dilution refrigerator. And so this just gives you an idea of how it's all installed. And so this is the magnet in its superconducting sheet. You have squids that were installed at 700 millikelvin, and it's all thermalized via this copper banding to the coldest stage of the dilution refrigerator. You have two options for how to couple your pickup loop in the center of the magnet. You can either directly couple it to the squid. In this case, this is a broadband readout. You see all frequencies all the time. That conceptually is very nice to see all of the frequencies in your detector all the time. It's also, from an engineering perspective, very easy. The other option is to do a resonant readout where you couple the pickup loop to your current sensor via an RLC circuit, where you get an enhancement in your signal by the Q value of your resonator. So this, if you can get a resonator for this RLC circuit on the order of 10 to the 6, you get a 10 to the 6 in amplification of your signal. That is very cool. These are very large capacitors and inductors. And so this is a non-trivial engineering task that I did not have any money for. So we went ahead and did the broadband readout. We'll talk a little bit more about, we can talk more about the RLC, the resonant readout later. So, so in the interest of time, here's some more pretty pictures of the detector, some wonderful mu metal shielding that was harvested off of MIT's old accelerator. And then the first results, which were a few years ago at this point. But the data is really beautiful from this little detector. And so what you see here is the frequency range that we were sensitive to. At the lowest frequencies, you're seeing this forest of lines. This is due to stray magnetic fields in the detector as the magnet shakes. Any stray fields from the magnet will induce an axion in your detector. At the highest frequencies, you're seeing the limits of our electromagnetic shielding. I told you it was harvested off of an old accelerator. This is not a precision Faraday cage by any stretch of imagination. But in this nice region from up to about 1 megahertz, we are right at that dotted green line, which is the theoretical squid noise floor for our readout system. And so for something that was sort of put together on a shoestring, it was a very nice result to show that this technique is really powerful going after squids. I would note, if you want to zoom in up at the top, an example signal on top of the noise in the experiment. And so once again, this is a very small signal that we looked at. The other sort of difficulty, and this is one of those times where difficult things get one slide in your presentation, was actually calibrating the system. Injecting an actual axion signal and trying to read it out with signals that small was challenging. So we did it. And this is the results of that first experiment. And I'm leaving out a lot of details on how we process the data. And so in this parameter space, what you see is the mass of the axion, the coupling to photons, and the first abracadabra result up there. And I point out sort of the scale of the ADMX experiment and the scale of the solar experiment that we're competing against. These are not tabletop experiments, and abracadabra was about the size of a grapefruit. So not so bad for a little grapefruit. We actually did a second run in the middle of the pandemic. We were doing our second run. Instead of using a simple pickup loop, we moved to a pickup cylinder, and this is to couple to more magnetic flux of the signal. It is an easy upgrade that involved just a lot of simulating to understand exactly what the efficiency was of this upgrade. And so I would note this was the work of our lead graduate student, Chiara Salemi, who was starting at Berkeley as faculty in another few months, and the junior graduate student, Callie Roy Pappas, who just started as a postdoc at Columbia. And this is the results of the second run of abracadabra. On the x-axis, once again, you have the mass of the axion, and on the y-axis, the coupling of photons. And you see that for some parts of the parameter space for the first time, we are beating the solar axion experiments. And once again, this is a very small experiment and showing you the power of a small demonstrator to actually go after new physics. So new techniques, enabling new physics searches. And I would also point out there was some very nice results from Alex Schutzgott's group, the shaft experiment, which was using slightly different techniques, but sensitive in the same parameter space. So that is the Abracadabra team. And so what's next is, as I said, when you're going after a result like this, things don't stay small. And so the next stage of this experiment is going to have to get bigger. And so the logical next stage is something on the order of a cubic meter of magnet. And that magnet costs around $8 to $10 million. And so this is no longer something that the Department of Energy or NSF will let a university do all by themselves. So we've teamed up with SLAC and a DM radio team led by Kent Irwin to realize the DM radio program. So what is that? So what the idea of DM radio is to actually do this definitive search for these nano EV axions. So what are we going to do? Is we're going to need bigger magnets. We're still going to have to do a good job on our cryogenics to get this whole thing cold. We're going to have to move to that resonant readout and the amplification, the sensitivity gain that you get with the Q value, and continuing to do a good job with vibration isolation and more meaningful shielding. And so we envision this program in 3 steps: DM radio 50 liter, DM radio cubic meter, and DM radio gut. So DM radio 50 liter is sponsored by the the Moore Foundation, and was in the design phases as we joined together. And so the Abracadabra expertise has really come in handy. In fact, our magnet vendor is the same magnet vendor that made the Abracadabra magnet, located about 10 miles that way. And so we've been involved, highly involved in the work on the magnet. And so it was in the process of being wound. All the parts are wound, and we are waiting to do some testing and some final design work on the support of the magnet. And so the parts of that are arriving and are being installed in January when the cryostat arrives. The next experiment is this DOE project, which is DM radio cubic meter. This is the meter cubed magnet. And in order to hit DFSD with that scale of experiment, you have to move to higher frequencies. This is a trickier frequency range because you start breaking down the quasi-static approximation. So we've actually had to do a lot of work on the simulation of this environment to understand how to actually read out the signal and not end up with various modes of the cavity that we're using to read out this thing. So this has been a lot of fun with ComSol, led by a combination of students, Alex Rosser at Berkeley, Nicholas Rapidas at Stanford, and Josh Foster, the postdoc, a Populario Fellow, now faculty at Wisconsin, to understand this and what series of different size coaxes we'll need to read out the experiment. And so finally, the gut scale program. At this point, how do you actually make it down to DFSD at 1 nano EV is a long-term R&D program. And so it's going to require very large magnets, and it's going to require coupling them to quantum sensors that are operating beyond the standard quantum limit. So that is what we've been working on, which is understanding exactly what magnetic field you're going to need, with what volume, with what level of quantum sensing to reach a scan time or an experiment that can run in under a decade. And so this is all something that started on the tabletop, and in order to actually go after this physics is going to be something much larger than a tabletop. But what's really fun about these sort of projects is how it overlaps with other technologies. And so what I would note is that though these magnets are big, it's highly overlapping with the magnets that are needed for fusion. And for those that don't know, one of the large fusion efforts is out at Devens, which is about 20 miles that way, to actually realize these new high temperature superconducting magnets for fusion. And we are trying to understand how we could put coupled into that effort. So the other question you might ask is, what can we still do with Abracadabra? And so that's the beauty of having something that is in the lab and can turn around results more quickly. And so what we've been doing is actually looking for high frequency gravitational waves with Abracadabra. There is some coupling of gravitational waves to electromagnetism, and you would see a modification of the signal in our detector. And so that is a configuration that we have set up and run. It turns out that in order to see these transient signals, we have to digitize constantly. We can't just stack up our Fourier transforms. This is a lot of data that comes in quickly. So this became actually a data analysis problem, not a detector design problem. And so this is the work of Callie Roy Pappas, and that result will be coming out soon, and it's really neat. And so that is DM radio. That is how something that started on the tabletop gets you to gut scale and beyond the standard beyond the standard model physics. With that, I think I got us home on time and would like to take questions.
Very technical question.
Yeah.
So in your abracadabra setup, you have magnet on the DR, right? How much current do you supply to that magnet, and how do you manage the heat flow?
It's a superconducting magnet. So it's 120 amps that goes in once. The fridge, the leads are all thermalized at the 4 Kelvin stage where we have enough power to take that heat.
How about the connection from 300K to 4K?
The magnet is sitting at 4K.
The lead from 300K to 4K is copper or
What?
the feed through from feed through
Yeah.
to like 4K stage
Mhm.
or 7K stage, whatever the
Yeah.
stage. That must be normal conducting.
It is normal conducting to 4K, and there's a superconducting switch. And so you power on, you cool down everything and you send the power in, and it sends the power down to the magnet.
I see, okay.
But
But my question was the heat load from that, at that room temperature part is also negligible or manageable from the.
it is manageable, but that is why that superconducting switch sits at 4 Kelvin and not 10 millikelvin.
Okay.
You don't have the cooling power at 10 millikelvin.
Okay.
And the whole magnet sits actually closer to 750 millikelvin, not because you're not supposed to use a dilution refrigerator like this.
Right.
But I didn't have the money to engineer a separate system, and that's actually, if you ask what the difficulty of 50 liter has been, it's been learning how to do that engineering of the magnet sitting at 4 Kelvin and the dilution unit cooling the tuning components at 10 millikelvin. And that's what actually my student Jessica is really in the middle of doing, is the design of the 20 millikelvin. Yeah. But those are all good questions, and it only works because you're dumping that power up at 4 Kelvin.
Thank you for the great overview of like the Axion landscape. This might be a bit of a naive question. You mentioned like scalar and vector dark matter. Does anyone look for tensor dark matter?
Oh God, this is a Masha question.
Maybe it's very hard to have spin to massive fields, which are weakly interacting. So if they're much less well motivated than we see there.
Thank you, Masha.
Question. Why does the DM radio meter cube line have a cheek? Like, why does it go?
Oh,
flat?
that's because you're scanning.
Yeah.
You just decide how long you're going to run at each of those positions. And so,
Why wouldn't
yeah.
you run longer and make it all the way down? Is it like a block?
so there's also like the sensitivity, you're sorry, it's not, sensitivity goes as T to the 4th or something, so you reach your sensitivity almost immediately. And so the question is, you could keep scanning this way with more time, sorry. You could keep scanning this way with more time. Your sensitivity here is basically set by your magnet volume. Right, and so when you're dealing with the scanning, it is a question of how many points you scan at, given the envelope shape of your resonator and all of this. There's an entire tome of 150 pages outlining exactly the strategy for this. But yes, the ultimate sensitivity of how deep we can go is determined by the B times V of the field. And then how far we go along that is the scan time. So it kinks up because we don't have to scan as long. We don't have to spend as long scanning at those higher frequencies.
Do you have a sense of if I wanted to get down to the DFSS line, how much longer would I have to run the experiment?
I think the answer is we can't go much farther because the magnetic field is not big enough. Yeah. And so that's why the pink line starts going down there, is that's the 10 meter cubed, 10 Tesla magnet. That can get down there. So yes, but that kink structure is your scanning strategy convolved with your magnetic field is the correct.
Last question. Yeah.
I can probably see it from the plot, but I'm just curious, between the gut and the meter cube, where they overlap,
Mhm.
which experiment is more efficient or more sensitive?
The gut scale, it's just a gigantic magnet. And so I think this actually is a nice way to tie it back of sometimes the brute force approach is just what has to be done. And so in this case, the improved readout and the improved, the improved readout and our noise levels and all that can't overcome the fact that there's just not enough D times B to get down there. But yes, I'm sorry, what we're completely worried about on DM radio meter cube is that we're probably going to focus more right here. And try to save some money and not run all the way down there. That's why I went to that question. I'm like, oh no, they're asking about the one thing I don't want them to ask about, but no, that's not it. Well, thank you, everybody.
Let's thank Lindley and all the Kickstarters. And also, since I'm up here, I just want to thank the organizers for a really
Yeah.
wonderful workshop. So thank you guys.
Bye, everybody.